Hello everyone, I'm Norman Wildberger, and this is part of a series where we're looking at the sociology of pure mathematics. And last time I talked about the first few propositions in Book 1 of Euclid, the most important and famous text in mathematics of all time. Today I want to go a little bit further and talk about the next three propositions in that book, which are also of a kind of theoretical nature like the last two that we've been looking at. And they also provide challenges for us to try to determine whether these things are really valid. The results themselves are actually quite important and relatively simple to understand, but whether the proofs are valid or not is an interesting question. So we are going to touch base with some sociological issues at the end of the video. Okay, so proposition number 6. It's called a theorem, and it states, if two angles of a triangle are equal, then the sides subtending the equal angles will be equal. So this is called the converse of Pons Asinorum. So we're talking about a triangle like this one here, and the theorem says that if this angle ABC right here equals the angle ACB right here, then the two sides corresponding AB and AC are equal. So a few things just to remind you that when Euclid talks about angle, he does not talk about an angle measurement. He is not referring to the result of a protractor measurement. Okay? He's thinking about this as a geometrical object, a planar geometrical object consisting of the wedge between these two lines. And Pons Asinorum is the converse, saying that if the two sides are equal, then the corresponding or subtending angles are equal. This is the first example of a proof by contradiction in Euclid. So it's a very important example of a proof technique in mathematics, which is maybe a little bit contentious. Some people are not so agreeable with the idea of allowing this. All right, so let's have a look at Euclid's proof of proposition 6. And for fun, I'm going to sort of read Euclid's proof to you so you get a sense of his language. This is from my edition by John Keel that I've told you about before, published in 1723 from the Latin translation of Commendine. Okay, so he starts, let ABC be a triangle, having the angle ABC equal to the angle ACB. So that's our assumption. I say the side AB is likewise equal to the side AC. That's what he wants to prove. 4, if AB is not equal to AC. So here he is introducing this proof by contradiction. He's saying, okay, I want to prove that AB equals AC. So if AB does not equal AC, then he's going to make an argument which will ultimately result in a contradiction, and then going back to the start, that will then prove that his assumption was incorrect and AB does equal AC. Okay? So the first case, perhaps in mathematical history, of a proof by contradiction right here, proposition 6. Okay, so he's saying, 4, if AB not equal to AC, let one of them as AB be the greater. Okay, these two are not equal, so one of them is bigger. Let's suppose that AB is bigger than AC. From which cut off BD equal to AC. So cut off BD equal to AC. And join DC. So we are setting BD equal to AC. Okay? We're assuming that AB, this segment here, is bigger than AC. So if we move along here up to a place where we can get something equal to AC, and remember that was one of the constructions that he's already alluded to in an earlier proposition, that if we've given a segment here in a certain direction, we can lay out on this segment a segment equal to the given one that we're thinking about. Okay, so there's a construction underlying here. He's not saying so, but there's a prior construction that he's using here. So we've located this point D, has the property that BD equals AC, and now we've joined D with C. Then because DB is equal to AC, and BC is common, DB and BC, DB and BC will be equal to AC, CB, each to each. Okay, let's pause and think about that. So what is he saying? He's saying, therefore, because look at the two triangles. Maybe I'll just interject some explanation here. So look at the triangle, say DBC. Here to here to here. He's basically saying that this thing is equal, or maybe I'll put a wavy equal, because it's not entirely clear what Euclid means by equal. It's equal to the triangle ACB. That's basically what he's saying there. So what's the justification for this? So the first side of the first triangle, DB, is equal to the first side of the second triangle, AC, because we've arranged that. Okay? The side BC is common to both. Right? That BC there is part of the first triangle, and it's also equal to the second triangle, that segment of the second triangle. And furthermore, the angles are equal. Okay? The angle between this side and this side of the first triangle is this angle right here, and that's equal to the angle here, which is the angle between the first side and the second side of the second triangle. So now what we're doing, or now what Euclid is doing, is he's using a prior proposition. Again, he doesn't state this explicitly, okay? But he's using the prior proposition, I think it was proposition 4, that said that if you have two triangles and their sides are respectively equal, and the contained angles are respectively equal, then the triangles are equal. Okay, and then he explains, and the angle DBC is equal to the angle ACB from the hypothesis. Therefore, the base DC is equal. Therefore, the base DC is equal, and the base to the base AB. So the consequence of that is that this side here, DC, which is the third side of the first triangle, DC here, is equal to AB, this side of this triangle here. And the triangle DBC is equal to the triangle ACB. That's sort of what I've just said there. Apart to the whole. These are equal apart to the whole. So he's saying these two triangles we've established are equal. Okay, but we can see that DBC, this triangle here, is contained inside the triangle ACB. So when Euclid refers to two triangles being equal or two regions being equal, typically he's referring to the areas being equal. Okay, and that's what's happening here. So it's really a question of areas. But how can this smaller area be equal to the bigger area that it's contained in? So he says apart to the whole, which is absurd. Okay, he uses that phrase, which is absurd. Therefore, AB is not unequal to AC and consequently is equal to it. And then the last paragraph is just a repetition of the statement of the theorem. Okay, so that's the contradiction right there. Okay, that's the contradiction. And so therefore the conclusion is that the assumption that AB does not equal AC that assumption is actually incorrect. which tells us that, therefore, AB actually does equal AC, which is what we are trying to prove. All right, great. Now let's have a look at proposition 7, another theorem. It says that on the same right line cannot be constructed two right lines equal to two other right lines at different points on the same side and having the same ends which the first right line has. Okay, that's a little bit hard to understand. The picture makes it much clearer. So here's what he's saying. So we're starting with this right line AB, and right line means segment, okay? And on this segment, we're constructing two right lines, say AC and BC, okay? That's one pair of right lines. And now there's another pair going to D, AD and BD. And he's saying that it's not possible for us to do this in such a way that AC and AD are equal and BC and BD are equal. Okay, so what we're going to do is we're going to suppose that AC equals AD. So AC equals AD. We could maybe denote that by putting some lines there. Those two segments are, we're going to assume, equal. And BC equals BD. But C and D are actually not the same point. So he's saying this is not possible. It's not possible to come up with such a configuration. And then he wants to come up with a reason. Okay, so we might start by just joining C and D so we have some more triangles to work with. Now let's have a look at what Euclid uses for his proof. Okay, so after introduction, sort of setting this up, then because AC is equal to AD, the angle ACD will be equal to the angle ADC. Okay, so since AC equals AD, from that, we conclude that the angle ACD equals the angle ADC. Pause for a moment there. What's he doing there? ACD equals ADC. That's right. So he's saying that this angle is equal to this angle because in this triangle ACD, these two sides are the same. So that's Pons Asinorum. You have two equal sides. The corresponding angles have to be equal. Again, he's not referring to which propositions he's using. He does that throughout, so you are expected to, have paid attention to what's gone on previously and recognize, aha, we're using this result that's already been established. Okay, and consequently, the angle ADC is greater than the angle BCD. So therefore, he's saying the angle DC is greater than the angle BCD. The angle ADC, this one right here, is bigger than the angle BCD. Right? The angle BCD is that one there. Okay? And you can see that in this case, that's less than the angle ACD because that segment, that sort of the wedge-like segment emanating from C in that direction is less than the bigger wedge coming out this way. Okay, wherefore the angle BDC will be BDC will be much greater than the angle BCD. So therefore, the angle BDC, and he uses the term much greater, so I might use a double equality there, a double inequality to denote much greater. So angle BDC is much greater than the angle BCD. Okay, why is that? So the angle BDC. That would be like this one here. Maybe I'll make it dotted, okay? That one is clearly bigger than the angle ADC. The angle ADC is equal to the angle ACD, which is bigger than this one BCD. So we're comparing this dotted one here with this one here. And it's greater, much greater, because there's actually two inequalities that he's referring to. He's referring to the fact that this BDC is bigger than this angle here. Okay, and then the angle ADC, you can see that because this segment here is bigger than this segment here, this angular segment. So there's an inequality between these two, and then there's the corresponding inequality between these two. Okay, but again, because CB is equal to DB, because CB equals BD, the angle BDC will be equal to the angle BCD. Okay, so we can say, but because there's another isosceles triangle here, the triangle BCD is isosceles, so the fact that BC equals BD, that should imply, using Pons Asinorum in this triangle here, that these two angles are actually equal. That angle BDC should equal angle BCD. Okay, and I'll put an X here to mark, well, that's a contradiction. Okay, because we've just established that angle BDC, this one here, is actually bigger, in fact, much greater than angle BCD. So it's another argument by contradiction. And we have to acknowledge that maybe a modern reader would be a little bit nervous about this because it relies quite a lot on the diagram, doesn't it? It requires us to have the things in a certain position. You know, if B was somewhere else, you know, it's not so clear. And also the fact that all of this is happening on the same side of AB, which is one of the initial assumptions. Okay, on the same right line cannot be constructed, two right lying on the same side. If we had put D on the other side of AB, then the argument would no longer work. So where in the argument were we actually using that particular fact? It's also not so clear, is it? So I think it's safe to say that a modern student, while he can appreciate that there's something pleasant here and it's a clever argument, which does rely on the previous things that have been established, it's not entirely really watertight. All right, and the third of the propositions that we're going to look at today is proposition number 8, another theorem, which is that if two triangles have two sides of the one equal to two sides of the other, each to each, and the bases are equal, then the angles contained under the equal sides will be equal. This is, in modern formulation, usually stated another way. It's usually stated that if three sides of one triangle are equal to three sides of another triangle, then those triangles are congruent, meaning that also their angles are respectively equal. So he frames it in terms of, you know, having bases, a triangle is built on a base. Okay, I'm not going to go through word for word the argument. I'll just give you a rough idea. It's a little bit similar to what we've been talking about. So here's a triangle ABC, and let's suppose that we think of the base as BC, okay? And this side here is, let's go over here. Here's the other triangle EFD. So we're assuming that A, B, and C are sort of in the same relation as D, E, and F, meaning what? That AB is the same as DE, and AC is the same as DF, and this base BC, okay, is the same as the base EF. Okay, then we want to show that the angles contained under the equal sides will be equal. So what Euclid does to prove this is he uses an idea of a sort of a transformation. So he says, in modern language, something like this. Okay, suppose that we take this triangle ABC. Think of the base as being BC. And we move it so that its base is EF. So we impose it on EF so that it has base EF. So that it's the image of A will be G. Okay, so now we've moved this triangle ABC, so its image is on top of EF, and the other endpoint is G. So that would mean that EG is also equal to this thing here, and this one here is equal to this one here. But because we've moved it, the angles in this triangle EFG are exactly the same as the angles over here, because we've just moved the entire thing. Now, he wants to say now, okay, that actually it must be that D equals G. That this moved triangle that we've moved, as long as we've moved it in the way that the side of EF that we're moving it to is on the same side of EF as D is. Okay, then we end up with a configuration like this, and it must be the case that D equals G. And why is that? Well, because it's exactly the situation in the proposition that we've just proven. Okay, here we have a base. Here we have 2 points on the same side of that base. And these two sides emanating from E are equal, and these two sides emanating from F are equal. And we've just shown that that's impossible, that if we have such a configuration, D and G actually have to coincide. Oh, that's the gist of the argument. It's also really another argument by contradiction. So we really have 3 arguments by contradiction right after each other here in this book 1 of Euclid. So let's have a look at some of the logical issues. There are clearly some logical issues that we have to address here. And I want to make it clear, that I'm coming from a position of great respect and admiration for Euclid. His fame and the historical importance are well deserved. But from my point of view, what Euclid was accomplishing was setting up a basis for a kind of applied mathematics of the geometry of everyday life. That's a different issue from how successful is what he's done in providing a framework for modern sort of abstract, pure geometry. That's a really important issue that we need to talk about. So without wanting to criticize Euclid too much, I do still want to point out that there are logical issues here that are preventing Euclid really from being a proper foundation for modern pure geometry. For example, there's the lack of clear definitions. We have this feeling that we're not exactly sure what the objects really are. Okay, points and lines maybe, angles not so much, areas haven't been defined. What do we mean by the side of a segment? Have we defined what that means? There is definitely a reliance, perhaps it's implicit, on diagrams. If you have the arguments in front of you and there's no diagram to support them, it's much, much harder to understand what's going on. Absolutely clearly, right? And then there's this use of transformations, the idea of taking an object and moving it to some other place, transforming it in some kind of way, and then talking about various properties that have been preserved. But we haven't addressed this fundamental question of, what is the kind of transformation that we're considering here? Do we have a prior theory of transformations? That's very easy for us to enunciate because in the 19th century, the importance of a transformational approach to geometry became very clear. So us moderns are naturally oriented to thinking about transformations as being really important concepts, and we want them to be nailed down very clearly. Okay? So we can see the absence of that in Euclid immediately. There's also another kind of issue here, which is sort of like the chicken and egg kind of issue. What comes first? Is it the chicken or the egg? In the mathematical context, there are these two things. There's mathematical definitions. You know, have some formal mathematical definition of something. And then, on the other hand, you have the usage of that concept. So it's an interesting question, which of these comes first? Do we actually start with the definition, you know, and then from that we build up enough understanding to then be able to use it in some context? Or do we rather use something, perhaps somewhat informally, and draw pictures and, you know, and make arguments informally, and then after a certain point think, well, actually we need a definition to support this. Now let's cook up a definition that will capture whatever it is that we think we're doing here. Okay. There's an aspect of this question. This is a very fundamental question that runs through a lot of the thread of modern and not so modern pure mathematics. The role of definitions. Are definitions coming first, or are they sort of add-ons that we put on, sort of, you know, to give a stamp of approval to our theories to make them look logical? Oh, now we have a definition that supports what it was that we were doing before. Okay, there's an interesting question in that direction. We might talk about that more with some other issues too. Okay, so now we come to an important question that's really very important for the sociology of pure mathematics. So geometry has been this central subject in mathematics, arguably the most important single subject in mathematics throughout its history. And for most of that history, Euclid was the logical foundation for it, and the authority of Euclid was not really challenged until the 19th century. Well, we see the beginnings, the rumblings of discontent already in John Keel's day, but really only in the 19th century did this get going in a big way. And then at the end of the 19th century, even educators started to abandon Euclid in a big way. Okay, the 20th century has seen a huge decline in Euclid, and partly, at least, that's because people have started to recognize this issue that the question is Euclid's Elements really a proper foundation? Is it a proper foundation, a proper logical foundation for geometry? And if not, then what is? Okay, so if we're going to admit that Euclid has some problems, then what are we going to do about that? Are we just going to say, well, that's too bad, you know, or are we going to actually try to create a different framework? Well, obviously, as pure mathematicians, we're obliged to attempt a proper framework for the subject. But this is sociologically a very delicate issue because Euclid has almost a religious position in the pantheon of mathematical history. Okay, it's really been hard for people to stand up and say, you know, I think we need to look at alternatives. You can see how John Keel reacted so strongly against people of his day that were trying to buck the system, according to what he was thinking, and provide alternatives. So it's a very delicate issue, and it's quite interesting sociologically about what do people really think about this. This is not something that I've seen discussed very widely in mathematical circles. It's just something that we would rather not talk about. So we pay lip service to Euclid. So if someone says, well, that's in Euclid, no one says, yeah, but Euclid, no one says that. No, you have to say, oh, it's in Euclid, okay, you know. But sort of everybody knows in modern times that Euclid is not really an adequate foundation. But what is? Well, it's not as if people haven't been thinking about this. So people have been thinking about this, of course. And David Hilbert famously gave a quite interesting attempt to create a different or better foundation for geometry. Another development, which I think is even more important, is the development of modern linear algebra, which is not really so much necessarily in the geometry direction. It has other interests in terms of algebra and you know, other computational issues. But it turns out that modern linear algebra somewhat naturally provides a pretty decent alternative framework for geometry. So that's another thread in this discussion. And then if we go to the 21st century, well, we have rational trigonometry. and universal geometry, which allow us quite novel ways of trying to really solidify what's going on with geometry. So there's a lot of interesting developments, a lot of questions here that we get by studying Euclid. I'm Norman Wildberger. Thanks for listening.